Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. This video is part 2 of human-machine interaction, focusing on alarms. In Hollywood movies, if the scene opens in a control room, expect multiple horns or klaxons and banks of flashing red lights. Something's gonna blow. Go to YouTube and search for China Syndrome control room scene, which I would show you here, but there would probably be copyright issues. This movie is from 1979, so the control room is hardwired and analog rather than graphical and digital, but it does depict a nuclear power plant control room of that era. And the process issue causing the near disaster is unreliable level measurement, which is a realistic problem I mentioned in my lecture on sensors. But the key thing I'd like you to watch for is how the alarms and confusion build tension and fear. That tension and fear, which is exactly what Hollywood was trying to create in the scene, of course, but the tension and fear depicted there help set back carbon-free nuclear energy for 2 generations, for which we are paying the price and will be for generations to come. In real control rooms without Jane Fonda and Michael Douglas, tension and fear are deeply undesirable. There are many alarms, most unimportant, triggering frequently. Alarms need to be noticed and dealt with calmly. Different levels of severity deserve different levels of attention. What we will talk about in this lecture is how to manage abnormal process situations, how to alert operators, and how to make it easier for those operators to succeed in managing those situations. What is an alarm? An alarm is a binary condition, true or false, usually indicating an unusual situation, usually accompanied by a visual or oral indicator. The standard analog input has 4 default alarms, low and low, which are less than or equal to alarms, and high, which are greater than or equal to alarms. The trigger value can be either a constant or a variable generated by a formula, which can be generated by any combination of math and logic that you can compose from the process data, so you're limited mostly by the measured data and your imagination. Alarms always have a deadband. If an alarm switches from false to true as the value exceeds its trigger point, the deadband is the difference, measured generally in percent of full scale, that the value must be less than its trigger point before the alarm switches from true back to false. So if a high level alarm on a tank is set to 80% with a deadband of 1%, the alarm status will become true when the level reaches or exceeds 80% and will switch back to false when the level is less than or equal to 79%. Because process data is often noisy, a deadband prevents alarm chatter, which is an alarm triggering and untriggering frequently as it sits near its trigger point, which quickly becomes a nuisance. Have standard deadband values for different types of alarms and modify them appropriately to avoid nuisance alarms if you find that nuisance alarms are happening. All Boolean or digital sensor data or variables can be configured to trigger alarms. For instance, a digital sensor to detect a blown rupture disc, or a high point level sensor to signal a tank overflow. As discussed in the digital constraints lecture, any logical expression which evaluates to true or false can be assigned to a Boolean variable. That expression can trigger an alarm as easily as it can trigger an interlock. Digital expressions can't have a deadband, but they can have delays, which are useful in preventing nuisance alarms. An example is a digital high-level probe in a distillate or bottoms tank for a distillation column. The tank is fed from above with liquid near its bubble point, and the receiver is small, so the probe is necessarily near the liquid inlet. Splashing is to be expected. A receiver overflowing raises serious safety and equipment concerns for the column, so an alarm, if not a column shutdown, should be triggered when the high-level probe is immersed. But in normal operation, the probe may get splashed every several minutes and show a high level for 5 to 20 seconds before reverting to normal, despite all of this time a normal level being present in the receiver. So what's the solution? You do want to have a level probe as a backup to prevent an overflow. So the solution to this is to add a delay such that only if the probe shows high level for 30 or maybe even 60 seconds is an alarm or interlock triggered. How long to set delays, or for that matter, how big do you set your deadband? This often depends on the specific geometry of a process. You can have standard practices, but you may find a particular instance is going to be different. Documenting and eliminating nuisance alarms is a task that can take weeks or months after a startup, but it is essential. A control room with lots of nuisance alarms is a control room where alarms get ignored or turned off, which is a failure of engineering at least as much as it is a failure of the operators and their management. Even if we succeed in eliminating most nuisance alarms, operators in a normally running process will often see many alarms in an hour due to normal status alerts of normal changes, sensor noise that quickly reverts to normal, or legitimate deviations that feedback and digital controls cope with automatically, but are nevertheless still alarmed. When something actually goes wrong, often many alarms are triggered simultaneously, because a high temperature can lead to a high pressure or a high level, because everything in a process interacts. An alarm manager is a repository that lists all of the current and past alarms. It tries to sort them by priority, by unit or process area, and by time, but it's still just a list. Many incidents, including the fictitious one in the China Syndrome movie, feature operators staring at lists of alarms, trying to figure out what's happening. It helps if the plant has a descriptive tag numbering system, so that high temperature in reactor 31 is recorded as TT-R31.high alarm rather than TT-42569.high alarm. But the list of alarms in an alarm manager is more often useful in postmortems than in the heat of the moment. Much more useful as a communications tool for alarm and crisis management is the large process overview screens discussed in the previous lecture on graphics. If alarms appear on a process schematic, color-coded as to their severity, the location of the problem will be immediately apparent, which makes it much easier for an operator or engineer to understand, react, or troubleshoot. Always color code and animate alarms on process screens. So for instance, show process data in low or high alarm with a yellow background, and low and high alarms, color them red and blinking. And then when you're assigning the alarms, use the low and high alarms for warnings, and low and high alarms for actual unsafe states where action is being triggered or action is required from the operator. Which brings us to alarm types. We need to classify operator alarms to help him or her deal with them appropriately. The first is a normal prompt. The process is operating normally, but the operator's attention is required to perform a manual action or give permission to move to the next phase of a batch. Normal prompts are low priority. and should be communicated in a low-stress manner that won't be confused with a process upset. Neutral colored screen pop-up or a soft bell would be an appropriate sort of signal. Next, we have process warnings. These warn the operator that the process is close to the limit of its safe space in some dimension of the state. We want the operator to notice and investigate and use their judgment as to whether or not they need to act. Data backgrounds turning yellow is a typical warning prompt. Abnormal equipment state alarms result when a device is not in the state that it was commanded to go to, like a valve that doesn't close or a pump that doesn't start. We need the operator to notice, retry manually, pause or shut down the process if necessary, and troubleshoot. So if open valves and running pumps are white and closed valves and stopped pumps are black, making those with abnormal equipment states a bright yellow or green should attract the operator's eye. Troubleshooting pieces of process equipment that fail to follow commands is a very common and important part of any operator's job. Prompt response by them can avoid a temporary process shutdown. Next, we have abnormal or unsafe thermodynamic state alarms. An unsafe state either triggers an automatic response, ideally, or triggers an alarm which signals the need for an operator response. The operator needs to quickly assess the situation, make sure the process is moving to a safe state, often by shutting down or pausing feed, and then assessing whether the unsafe state is real or fictitious, and whether a restart should be attempted. These are the alarms where blinking red lights and audible alarms are justified, but go easy with the audible alarms. Once alerted, no operator is helped by having a loud horn going off as he or she is trying to manage a crisis. Give them a silence button. A safe process is one that shuts down automatically, not one with 5 horns ready to blare. Further notes on alarms. Most plants have too many alarms, which makes them a nuisance that is too often ignored. Alarms should be the product of a process hazard analysis, or PHA, where a team of engineers, operators, and other experts identify hazards, decides how to measure those hazards, and decides how the process and operators need to react when that hazard occurs. Don't just alarm everything because you can. On that note, serious hazards should trigger automatic responses. Operators startled and stressed by alarms often can't decide what's wrong or don't follow training and procedures. If you know what should be happening in an unsafe situation based on process measurements, have the automation do it quickly and automatically. Let the operator figure out what's wrong after you're in a safe state. 10 unnecessary automatic shutdowns are much cheaper than one necessary shutdown that didn't happen because it wasn't automatic. Alarms and interlocks must be descriptive. When something serious is happening or an automatic action has been triggered, spell it out by means of messages on the screen, clear indications of what devices are locked, and interlock descriptors for those devices. The operator will fight your system if they don't understand what is happening. Finally, eliminate nuisance alarms. Nuisance alarms are caused by poor design, degraded sensors, or unplanned for changes. There must be a system for documenting and fixing those nuisance alarms, particularly after a startup when they are inevitable. Remember the story of the boy who cried wolf. If operators start to think most alarms are fictitious, they will ignore not only those, but the ones that are real. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. Find videos on YouTube by searching for Process Control Design and Practice. Like and subscribe. I'm Tom Meadowcroft. I hope to see you again soon.